Welcome to Atoms to X-rays, a series about new developments in the physical sciences. Atoms to X-rays is brought to you by the Division of Physical Sciences and the San Diego Foundation's Reuben H. Fleet Foundation Fund, sponsors of the Atoms to X-ray website for teachers and students. Please visit the site and let us know what you think. We hope you enjoy the program.
Our speaker today is Mike Norman, and without question, I think some of the people in the audience would agree that he's one of the world's leaders in computational astrophysics. He came to UCSD last year from the National Center for Supercomputing Applications at the University of Illinois, where he was a senior research scientist and team leader. He received his bachelor's degree in astronomy from Caltech, his master's and his doctorate from UC Davis, and he's also worked at Lawrence Livermore Laboratory, Los Alamos, and the Max Planck Institute for Astrophysics. His talk today is entitled Cosmic Voyages Through Computer Simulation and Visualization. Mike?
Well, thank you, Kim, for that nice introduction. It's a pleasure to be here. This started when Kim suggested that I show some of my nice computer animations. And of course, I'll do that, otherwise you'd all be disappointed. But in so doing, I'd like to tell some science stories as well. My topic is the universe at large, cosmology, the Big Bang, the formation of galaxies, and so on. And I've entitled my talk, Cosmic Voyages Through Computer Simulation and Visualization. In this talk, you will see a combination of art and science in a very lovely way that depicts the state-of-the-art of our knowledge about the structure of the universe on the largest scales, as well as how that structure is formed through physical processes, which I will also attempt to describe. I'll start by just describing what astronomers know about the distribution of objects in the universe. And the key fact that you should take away is that there is a hierarchy of structures in our universe that spans a scale of over 1 billion in length scales. And we'd like to know where that comes from. Secondly, I'll show you a virtual voyage, a computer animation that takes the best astronomical data that we know about the structure of our universe and does it up in a Hollywood photorealistic way. And this is the first time this has ever been done with such fidelity to the scientific data. This will give you an idea of how this hierarchy of structures fits together in one continuous camera move, as it were. Then I will talk about how astronomers probe the deep universe, that is, distances of 1 billion light years and more, and what they found about the structure of the universe on that scale. And interestingly, what they found is that the galaxies trace out a pattern in the cosmos that's very similar to a spider web, and it's called the cosmic web. It's an intricate network of filaments and walls and empty regions called voids that appears to extend as far as we can see. Then I'll turn to the little bit of physics in this talk, namely how gravity is responsible for creating those structures. And this is meant to be a tutorial at the level of high school students taking physics or the lay public. And then I will conclude by going back to the Big Bang and describing how galaxies are formed and show you a visualization that's based on a physics supercomputer simulation of the formation of galaxies. Let's begin here. Of course, when we look up at the sky, we see stars, but if we look deep enough, we see galaxies. Now, we can't see those with our naked eye, but astronomers using telescopes can do this. And what you see here is a very large patch of the sky surveyed with telescopes, and every dot on that image is a galaxy. There's over 10 million galaxies in this image, and what you notice is that they're not uniformly distributed on the sky. Rather, there seems to be some concentration of galaxies in various places. These are called galaxy clusters for obvious reasons, but there are also very interesting long linear features which are called superclusters. And it turns out that these superclusters are tracing out what I've called the cosmic web. Now, this is a depiction of the distribution of galaxies on the sky. We'd really like to know how the galaxies are distributed in three-dimensional space, and we'll get there shortly. Well, what I've shown you is the distribution of galaxies on very large scales, but the universe exhibits a hierarchy of structures on a vast range of scales, and we've been talking about this supercluster scale on length scales of about 1 billion light years. If we go back to the most humblest of stellar systems, we have clusters of stars, which we find in our own Milky Way galaxy. These are about a light year across. And we can find assemblages of stars on increasing scales. Dwarf galaxies, about 1/10 the size of the Milky Way. Big galaxies like the Milky Way, which are about 100,000 light years across. Galaxies find themselves arranged in small groups of 2 to 10, and groups are collected in galaxy clusters, and finally the clusters are arrayed into superclusters, which are these long chains of clusters that were shown in the last image. So a vast range of structures. It's natural to ask two questions. One is, where does this come from? Why is there this hierarchy of objects? And secondly, does the hierarchy end? In other words, if we could go another factor of 10, out to 10 billion light years, would we find yet larger structures, clusters of superclusters, for example? Well, we know the answer to that question, and the answer is no. This is where it stops. So you're looking at more or less the complete range of structures that stars inhabit in the universe. It's rather difficult to make a mental picture of this when you just have 5 or 6 static images. And so what I'm going to do now is show you this virtual voyage, which starts at the sun and moves out through the local star systems and continues to accelerate out of our galaxy and flies to the Virgo cluster, which is the nearest and largest cluster of galaxies to us. This is all based on accurate astronomical data, and the visualization was made by Donna Cox and her collaborators at the University of Illinois. This was rendered for a PBS NOVA program that aired a little over a year ago. So let's take this voyage. So this assembles data on all of these scales that I talked about. We start in the neighborhood of our sun, moving out through the local star systems. We're moving towards the Orion Nebula, which is in the sword of the belt of the constellation of Orion. This is about 1,000 light years away. And we continue to move on out past the Horsehead Nebula, which is a star-forming region in Orion. And now we wheel around, and we're now at distances of about 10,000 light years from the Earth, approaching another beautiful nebula called the Rosette Nebula, another star-forming region. And as we zoom right through the middle of it, you can see the hot, bright stars that illuminate the gas that they formed out of. As we continue our journey, we move past the Crab Nebula, which is not a star-forming region, but rather the remnants of a massive star that exploded in 1054, witnessed by the Chinese. And you'll even see a blinking pulsar in the center of that nebula. We've wheeled around now so that we can look back towards the galactic center of our Milky Way, and we're rising out of the plane. Now, this is the only part of this visualization that is not astronomically accurate. Of course, we can't get a view of our Milky Way galaxy like this because we're in it. So what the visualizers have done here is used another galaxy that is like the Milky Way. There are the large and small Magellanic Clouds, which are satellites of the Milky Way. And now we're moving out through the local group of galaxies, which includes us, the giant galaxy in Andromeda, as well as another galaxy called M33. We're about 1 million light years from Earth now, and in this galaxy we're going to fly right through another nebula, which is a star-forming region like the Orion Nebula, but vastly larger. We've now moved out into deep intergalactic space. We've left our local group, and we're approaching another small group that contains a couple of spectacular galaxies, M81 and M82. We're on our way to, this is M101, a giant face-on spiral, one of the most beautiful in the sky. And this is the Whirlpool Galaxy, another beauty. Now we're moving towards the center of our local supercluster, which is the Virgo cluster. This assemblage of galaxies over here is the Virgo cluster. And what we're doing is we're moving down one of these long, tenuous filaments in the distribution of galaxies known as superclusters. So we're flying down a supercluster at much greater than the speed of light towards the center of the Virgo cluster. Every galaxy position is accurate based on surveys by Brent Tully and others. Every galaxy image is correct. And here we end our journey by flying into the heart of the giant elliptical galaxy M87. As I was describing how big or how far away these objects were, it's appropriate to ask, well, how do we really know how far away things are in the universe? And to answer that question, we have to go back to one of the early pioneers in cosmology, Edwin Hubble. Now, Edwin Hubble discovered that the universe was expanding in 1929, and here's a picture of Edwin pointing to the Andromeda Galaxy. What he found is that every galaxy is moving away from us. That's evidence of the expanding universe. But he found something else. He found that the speed with which the galaxy was moving away from us was directly proportional to its distance, and this is known as Hubble's Law. Now, this is extremely useful because if we can measure the speed with which a galaxy is moving away from us using Hubble's Law, we have its distance. Now, naturally, this relationship has to be calibrated, and this calibration has been the story of the 20th century cosmologists. Here is the kind of data that Hubble collected. What you see here on the right is the same galaxy that we dove into in the animation, M87 in the Virgo cluster, a large galaxy. And what you see here is the spectrum of that galaxy, and these two little black lines, two little black streaks in this blur of light correspond to specific transitions in chemical elements in the stars of that galaxy. And what Hubble found is he could see this characteristic doublet, as it's called, in these galaxies, but as he looked at galaxies that were further and further away, they were shifted further and further to the red end of the spectrum. This is known as the cosmological redshift, and it is through the redshift that we derive the speed of the galaxy. So here is one of the simplest but most important formulae in all of cosmology, namely that the velocity of recession, which is just defined as the speed of light times the redshift z, is given by Hubble's constant times the distance. And this Hubble's constant has been measured to more or less 10% accuracy by the Hubble Space Telescope in the last 10 years. So armed with Hubble's law, and here is a depiction of it graphically, the speed of recession plotted versus the distance, and the points here show what galaxy data would look like. This law now allows us to infer the distance to a galaxy by measuring its velocity of recession through its spectral redshift. So the way cosmologists probe the deep universe now is to go back to that image that I started with 10 million galaxies, and for each galaxy, take its spectrum, find its redshift, and from that, figure out its distance. This has been going on for about 15 years now, and the surveys are getting deeper and more impressive. And what I want to do is show you the results of the latest Redshift survey. And the way this is made is shown in this diagram. Here is the Milky Way galaxy. The sun is some distance out from the center. We look up and down out of the galactic plane for an unobscured view of the cosmos. And what is done is to observe galaxies in slices of the sky and look very, very deep. This project, called the 2-degree field galaxy Redshift Survey, is the largest that has ever been done, and this is their result. What you see here is what's called a cone diagram. One cone corresponds to each one of these slices from the previous slide. We are at the intersection of those cones, and every blue dot corresponds to a galaxy. And so what is plotted here is the galaxy's position on the sky in some angle and its distance. And for scale, this is 1 billion light years. The Virgo cluster, which we flew to in the animation, is about there. So this survey is about 20 times as deep as the distance to the Virgo cluster. Now let me show you a magnification of the southern hemisphere slice. Here is 1 billion light years for scale. And what you see is this interesting pattern that I've called the cosmic web, where the galaxies seem to be arrayed into long linear features called superclusters, and these more or less circle regions that are entirely devoid of galaxies, known as voids. Some have described this as a soap bubble pattern, others call it a cellular pattern. We call it the cosmic web. Where does the cosmic web come from? Well, the answer is gravity. Gravity is the cosmic sculptor that has organized the galaxies into this pattern. And the mechanism is called gravitational instability. And what I'd like to do in the next 5 minutes is go back to basic physics, basic Newtonian gravity, and try to explain how this works. Let's recall Newton's gravity in its simplest manifestation. Let's suppose we have two equal masses separated by some distance d. Then Isaac Newton told us that the force between them will be inversely proportional to the square of their distance and proportional to the product of their masses. And so this mass here feels an attraction from this mass in this direction, and this formula is the force due to gravity. So the mass squared divided by the distance squared times Newton's constant g, which is a known number. The minus sign means it's pulling you in this direction. By Newton's third law of motion, every action has an equal and opposite reaction, this mass feels the same force but in the positive direction, and hence you have a plus sign there. That's our starting point for understanding the cosmic web. Now, we have a little ways to go. Now let's consider the next simplest case, 3 equal masses, also separated by the same distance d. Well, consider the force on this mass. Well, that force is the sum of the force from this mass and that mass. And we know that this force is minus g m squared over d. But it also feels a force from this mass, which is at a distance 2d from this mass. So we now have to add on a piece, which is m squared divided by the distance squared, which is 2d quantity squared. By Newton's third law, this mass feels exactly the same force but in the opposite direction. So it's the same formula with a plus sign. But now there's something interesting. This mass feels no force. The force on it is 0. And the reason for that is simple to understand. It's getting pulled in this direction in exactly the same amount as it's getting pulled in that direction, because the masses are equal and the separations are equal. So the forces cancel. So there is a tug-of-war going on this mass. And the net force is 0. Well, let's take this one step further and consider the forces in a finite but uniform distribution of masses. So each one of these masses has the same mass, m. They're all separated by exactly the same distance, d. We find that the force on the one in the middle is exactly 0 because all the forces cancel. We can take the forces by pairs. We can take this one, and we know that those forces cancel from the last slide. And then we say, okay, well, we have to consider the force on this mass from this one, and that's exactly balanced by the force from this one, and so on. So the force on the middle one is still 0. But now let's consider another mass. Let's take this one here. Well, the force on it is, let's take it by pairs. Let's consider these two masses. They're equal and equidistant, so those forces cancel. Then this one and this one cancel. When you get here, that cancels with this, so the net force is still 0. But now there's one more particle, one more point mass over here, and its force is not balanced out by a mass over here. And so this particle feels a net force in that direction. And this force actually increases as we consider these particles, and that's easy to see. If we consider this one, those forces balance, those forces balance, but now this particle feels an unbalanced force from this, and this particle. So it feels a negative force, and it's larger in magnitude. And so this is what the forces would look like in this finite but uniform distribution of matter. Now let's consider an infinite uniform distribution. Something very interesting happens. All the forces become 0 on all the particles. Now, how can that be? How can we see that this is true? And by the way, this was first explained by Isaac Newton in his Principia. It's easy to see how this must be the case. Imagine this line of masses extending to plus and minus infinity. Such a line has no center. Another way of thinking about it is any place on that line is just like any other place because the particles extend to infinity in both directions. So if every particle is the same, and if you pick any particle and realize that there is an equal and opposite force coming from both directions because they extend to infinity, those forces cancel and you have a net force of 0. It can't be anything else. And so this is an interesting case and a very relevant case to cosmology because we live in an infinite universe. It's a three-dimensional universe, if you like to think Cartesian. It's a four-dimensional universe, if you like to think Einsteinian. But this simple model applies in any direction you like. I could have shown a two-dimensional or a three-dimensional array of point masses, and as long as they were equidistant and infinite, you would conclude that the net force on any particle is 0. However, if we take just one particle and we displace it slightly, as I've done here, that's no longer the case. And that's easy to see. The particle was here. We move it a little bit to the right. Now it's a little closer to this particle than that particle. And because the force goes as 1 over the distance squared, the force from this particle is larger than the force from this particle. And so there is a force to the right, as indicated by this arrow. Because forces are equal and opposite, from Newton's third law, this particle feels a force in that direction. Now, this particle had no net force on it because it was exactly balanced by pairs. If we move this particle to the right, it's now a little further away than it was, and so this particle now exerts a greater force on it. And so there's a net force on this particle pushing to the left. And in fact, the forces on these particles are also not 0, but they decay away, and I just haven't shown that here. So you have forces pushing to the right and the left, and all you've done is you've displaced one mass from its perfect equidistant separation. One way of thinking about this is, if we consider this a region of space, we've made the density of particles in this part of space a little higher, which is why I have the plus sign here. It's a slightly denser region of particles here, and we have forces that want to bring those particles together. Over here, we have a lower density distribution of particles, which is a minus relative to the mean, and that creates a force that pushes them apart. That is the mechanism underlying gravitational instability. And all we have to do is go from this discrete representation to a continuous description where we talk about density of matter, rho. And so this line here is the average density of the universe. And if we have a slight overdensity in one region, like here, point C, then gravity will amplify that overdensity like this by bringing matter towards it. And likewise, if we have an underdense region, it only has to be an infinitesimal difference. Then the gravitational instability will empty out that region and create an even less dense region. And this is the basic mechanism that creates the cosmic web. So now let me illustrate this with real computer simulations. The first is not a realistic universe. It's a toy universe because it's easier to visualize. It's a calculation of gravitational instability in 2 dimensions. That is a surface. But it's not a flat surface, it's a surface of a sphere, which in cosmology is called a closed universe. So this little animation shows 2 things. It shows a balloon, which is expanding, which is connoting the expansion of this 2-dimensional universe. And what is going on here is when the universe is very small, I impose minute density fluctuations. And as the universe expands, I solve the equations of gravity and matter dynamics Now, it's a little hard to see what's going on, isn't it? That's because we're looking at this as the universe is blowing up in our face. It's much easier to see what's going on if we move into a frame of reference that's expanding with the expanding universe. So we're moving out at the same rate that the universe is expanding, and our camera, if you will, has a zoom wide-angle lens that is zooming out at exactly the rate that the universe is expanding. And what you see now is, relative to this expanding universe, how the minute fluctuations are amplified by gravity. And what you see is matter is pulled into linear filaments, which correspond to clusters and superclusters, and empties out of these voids. Now, that's not a realistic universe. When you do this in 3 dimensions, what you get is the cosmic web. So this is a computer simulation of a large piece of the universe with proper cosmological data that starts out with minute density fluctuations and has evolved forward in time to the present day. And what you see is a network of filaments and voids. And here, that same cube is shown to scale against the galaxy Redshift Survey data that I showed you earlier. The network of filaments and voids has precisely the same character and scale of cells as the Redshift Survey. So that's the cosmic web. There is another way that astronomers probe the deep universe, and that's to use the Hubble Space Telescope, which you've no doubt all heard about. Whereas these redshift surveys look at a large piece of the sky and they go out to about 2 billion light years in distance, the Hubble Space Telescope is observing the universe through a soda straw. It is looking at a very small patch of the sky, but by making very long exposures, the Hubble telescope can probe much deeper. It can probe basically as far as the galaxies go. And the most distant galaxy observed thus far is 12 billion light years away, so 6 times as deep as that blue cone diagram. Now, you don't see as many because you're looking through a soda straw, but what you see is what galaxies looked like 12 billion years ago, because light takes 12 billion years to get to us from there. And so this image here, which is called the Hubble Deep Field, is exactly what I'm talking about. Everything you see on this image, except for that thing there, is a galaxy. The big galaxies are relatively nearby, and the little blue things are far away. And by looking at them very carefully and sorting them according to distance, we can see what galaxies looked like at different times after the beginning of the universe. And that's shown here in this composite from the Space Telescope Science Institute. These are galaxies as they are seen today in the modern universe, some 14 billion years after the Big Bang. And in these columns, you see what galaxies look like earlier and earlier in the universe. So at 9 billion years after the Big Bang, that is 5 billion years ago, they looked like this. Here's 9 billion years ago, and here is 12 billion years ago. And what you see is they look like a mess shortly after the Big Bang. They don't exhibit this beautiful structure that we're accustomed to seeing. There are no big spirals. There are no uniform ellipticals. They look lumpy. And that is strong evidence that these galaxies form through a process of mergers. in theoretical cosmology, we have a theory called hierarchical structure formation, which says that, in this diagram, time is running down, that if we end up with a big galaxy, if we look back in time, we can see that it was actually formed out of the merger of smaller things. So if we want to start at the top of this diagram, there might be a dozen small subgalactic units, and as time goes on, these merge together and form larger and larger structures. Well, this hierarchical structure formation is a generic feature of the kinds of theoretical models that I deal with and all theoretical cosmologists deal with. And it's a model that one can program up on a supercomputer and see what comes out in detail. And so I'd like to conclude this talk, since I'm running late on time, with an animation which starts shortly after the Big Bang. It starts with a universe that is dense, relatively hot, almost completely smooth, except for the presence of minute density fluctuations that are too small to see. And this simulation solves the laws of physics for matter and gravity, and computes how these gravitational instabilities form small objects at first and how they merge together to form galaxies. This is also a visualization that was done by Donna Cox and her colleagues at the University of Illinois, and I supplied the scientific data that drives this simulation. So we start out with a universe that is bright and hot and almost uniform in its density distribution. It then expands, and as it does, it cools off, and hence the transition from white to red to blue in this animation. As the gas and matter becomes cool, gravitational instability kicks in, and you see small galaxies forming at the intersections of filaments of gas. And we're approaching a proto-galaxy group consisting of half a dozen or so galaxies. These galaxies are formed in the simulation by converting a gas to star particles. In other words, we have a recipe whereby we say this gas is dense enough that stars should be forming. Those are put into the simulation, and that's the result. So again, the universe is smooth and dense shortly after the Big Bang. We actually start the simulation about 100 million years after the Big Bang, and we stop the simulation at the present day, 14 billion years after the Big Bang. So time is elapsing at a rate of about 30 million years per second in this animation. The diffuse matter in the universe is colored blue in this visualization, and as gravitational instability collects dense pockets of matter, our simulation turns the gas into star particles, which form the visible galaxies of the universe. And one can see the dynamics of this structure formation is quite complex. You can see here are two galaxies orbiting around one another. A third galaxy comes by, and they begin to interact strongly. A fourth and a fifth galaxy move by. And the end of this is not an exploding galaxy, but an artistic effect where we just fly into one of the galaxies for show. The last topic, which is actually what I'm working on currently, and I think one of the most interesting questions that one can have in cosmology, which is what came first? If it is true, and it appears to be true, that large objects form via mergers of smaller objects, then one can ask, where did it all begin? What was the very first object to form that later became incorporated in larger objects? And what kind of object are we talking about? Well, I've been studying this with my former students and current collaborators, Tom Abel and Greg Bryan, and we have gotten an answer to both questions within the framework of our modern theories. And the answer is that the first things to form are what you might call microgalaxies. And each microgalaxy contains a single massive star. We call this the first star in the universe, but we're really talking about the first stars in the universe. What we've done is apply the kind of physical simulation that you saw in the animation to consider a very small patch of the universe, small enough that we can be sure that nothing is escaping our attention. That is, we can see the very first ripples growing into cosmic structures. That requires simulating a very small patch of the universe at very high resolution. And these three frames show what that patch of the universe does with time. You see the characteristic filamentary structure, and at the intersection of these filaments forms one of these microgalaxies. And in the center of this microgalaxy forms a single massive star. And what you see here are a sequence of images, each image 100 times magnified relative to the one on the left. So this is 100, 10,000, a million. And using very special numerical methods, we were able to follow both the large-scale dynamics of the universe at this early time and also follow the collapse of the gas down to form the first star or stars. And what we find is only one star forms per microgalaxy. The universe would be filled with these microgalaxies, but only one per microgalaxy. And these stars are very massive, about 100 times the size of our own sun. And so I'll conclude this talk by showing one last animation, which is a powers of 10 zoom from the cosmic scales in this simulation down into this microgalaxy, down into the molecular cloud that forms in its core, down to the first protostar. This zoom covers 10 powers of 10 in length scale. And it goes by pretty fast, so I'll play it again. And the simulation actually goes down two more orders of magnitude with a total dynamic range of 10 to the 12. With such a large dynamic range and resolution, we can be quite sure that only one star forms and it's a massive star. The implications of this are very interesting. Massive stars burn out in a few million years and they end their lives as supernovae. And if this is true, we shouldn't expect to see any of these first stars in the universe because they would have blown up long ago. Massive stars are also the place where chemical elements that you and I are made up of, elements heavier than lithium, such as magnesium, calcium, and iron. Massive stars are where these elements are created through fusion processes. And so these first stars in the universe will fuse the primordial gas into heavy elements and then blow those elements out into space when they go supernova, and thus seed the universe with the heavy elements that are required to form the next generation of stars, the planets around them, and eventually life. And with that, I'll stop. Thank you.
I think we have some time. I'm sure Mike will entertain some questions.
Love to. That's a great question. You're asking, where do these small perturbations come from? Well, let me answer that in two pieces. First, let me prove to you that the perturbations exist in the early universe, and then tell you what the latest thinking is on where they come from. This slide shows astronomical observations made by radio telescopes in Earth orbit in the microwave part of the spectrum. And what is being shown here is what is called the cosmic microwave background, which is the thermal relic of the Big Bang. This image up here was made in 1992 by the COBE satellite, and this is an all-sky map projected into this funny egg shape. And this is a much more recent observation made last year by the Boomerang satellite that provides high resolution in a piece of the sky. And what you see here in color is the fluctuations in the temperature of this cosmic microwave background radiation. These fluctuations are 1 part in 10,000. We know that this radiation is formed in the Big Bang, and the radiation that we see samples the universe about 300,000 years after the Big Bang. And so the fact that we don't see something that's perfectly smooth but rather rippled is proof that there were fluctuations in the matter distribution at such early times. These temperature fluctuations are proportional to matter fluctuations. And so, for all intents and purposes, one can say that this is a photograph of the matter fluctuations at 300,000 years after the Big Bang. And that's what we put into our simulations. Now, where do these fluctuations come from? This is where things get far-fetched, but still mainstream cosmological thinking. The idea is, and this is an excuse to go to this diagram, which I had to skip over. This is a diagram of the history of the universe on one slide, where this is a time axis starting at t equals 0, the Big Bang, and then moving out. This is just fractions of a second after the Big Bang, and the time scale expands as we move to the right. So this is a second after the Big Bang, 300,000 years after the Big Bang when we see this microwave radiation, 1 billion years when the galaxies start to form, and then here is the present universe. This scale here is the characteristic size of the universe. Since the universe is expanding, we can talk about the characteristic size scale at any time. And according to current theories, the universe underwent a phase of rapid expansion, exponential expansion, in the first 10 to the minus 32 seconds. That's called inflation. And then inflation stopped, and the universe kept coasting outward. And that's what Edwin Hubble discovered, is this coasting out phase of the expanding universe. The importance of this inflationary phase is that structures that were on subatomic scales would be stretched out into cosmic scales. And so the fluctuations that I showed on the previous slide were, at the birth of the universe, quantum fluctuations in the mass energy distribution of the universe at inflation. And so this is why I say it's far-fetched. But what's interesting is these quantum fluctuations should have a well-defined pattern of fluctuations, and that's precisely what's observed in the cosmic microwave background radiation. And so there's strong support for this notion from this and other pieces of evidence. Rick?
If your first stars only last a few million years, do they last long enough to merge with other things to form galaxies, or
No.
blow up first?
No, they blow up. And so what you're left with, well, think of it this way. I think of it as a field of daisies. What I showed you was one daisy. But imagine everywhere in the universe, these microgalaxies are forming. And they're not forming all instantly. They're forming a massive star, and then in a couple million years, that massive star blows up, basically creating a blast wave in its part of the universe. So in my mind's eye, what I see is sort of a field of daisies, a field of flowers that is seething, and the daisies are blowing up and sort of disturbing their neighbors. But no, each microgalaxy will puff out in this explosion. And what you're left with is in a universe filled with gas that's been enriched by these first stars. And those gas clouds will condense into larger galaxies with more stars. This remains to be computed and visualized. The question was, are my simulations using Newtonian gravity or relativistic physics? The answer is, it's all Newtonian gravity. Even though the universe in the large is relativistic in nature, as described by Einstein's general theory of relativity, we simulate a patch. And one can show that Newtonian physics is a very, very close approximation to fully relativistic physics, so long as that patch isn't as large as the cosmic horizon. And the cosmic horizon is just the distance a light wave can travel in the universe up to that time. So if we want to simulate the universe 1 billion years after the Big Bang, the cosmic horizon would be about 1 billion light years in size. But what's going on in the universe at that time is actually going on scales that is more like 1,000 light years. And so our simulation volumes are much, much smaller than the cosmic horizon at any instant in time. And so we're justified in using Newtonian physics. Yes?
You said that the supercluster filaments were the largest structures. Doesn't that imply that there's an edge to the universe and a center?
No.
It doesn't.
No. What it implies is that the superclusters are the largest things that can grow by gravitational instability in 14 billion years. With this hierarchical formation of structures in the universe, you start small and you build bigger and bigger and bigger. And so the superclusters are the largest things that gravitational instability can build in the age of the universe. And of course, that implies that in another 14 billion years, the superclusters will be yet larger. And that's undoubtedly the case, but how will we ever know?
I think we had a question.
Yes?
I was wondering why the structure seen at the supercluster level, why doesn't that carry all the way down to like the galactic level? What causes it to break down and you have galaxies as opposed to filaments now?
Again, this gets to how hierarchical structure formation works. The first things to form in the universe were these microgalaxies. And this is about 100 million years after the Big Bang. The most distant galaxies we can observe with the Hubble Space Telescope are about 1 billion years after the Big Bang. And by that time, the gravitational instability can work on larger scales, scales of about a few million light years. And then as time goes on, gravitational instability, so then you have a universe filled with proto-galaxies, but they're not arranged in superclusters. They're not arranged in clusters, probably not even in groups. And so this hierarchy of structures, galaxy, group, cluster, supercluster, is a time sequence. The galaxies form first out of mergers of subgalactic units, then groups form out of mergers of galaxies, clusters form out of mergers of groups in high-density regions, and then finally the superclusters are forming. So it's a time sequence.